Okay, should we start, Ronnie?
Sure.
Okay. You go back to presentation mode. Okay, good. Okay, well, welcome everyone to this first webinar talk of 2021, sponsored by the Chicago DOE Alliance Center. We're pleased to kick off the new year with a talk by Ronnie Bowler from Oak Ridge National Laboratory. Ronnie is likely to be well known to most of you if you're in the field of high pressure science or in high pressure geophysics because of his many contributions to both fields over many years. Ronnie has his degrees in chemistry and mineralogy from the University of Tübingen, and after obtaining a PhD there in 1974, he moved to UCLA, where he worked with George Kennedy, another leader in the field, known for many things, including his resistance to the diamond anvil cell, which he said would never work. So it was surprising then when Ronnie moved to Germany in 1986, he became one of the directors at the Max Planck Institute in Mainz and started a very impressive diamond cell program and made many contributions studying a lot of different materials and developing a lot of techniques that are in use today. And in 2009, we were able to lure him back to the States, and he joined our Energy Frontier Research Center in Washington, and there he began to explore pushing the limits of neutron scattering at very high pressure, and that led to a joint appointment at Oak Ridge and finally a senior scientist position that started in 2017. Ronnie has a number of awards, including the Schlumberger Medal, the Neil Medal, Fellowship at AGU, and he's a past president of AIRAPT, which is the International High Pressure Science Society. So Ronnie, we're really pleased that you're giving this talk today. It's all yours.
Okay, thank you very much, Russ, for the very nice introduction. Before I start, I want to wish everybody a happy and better new year. It looks good. I really have to tell you, Russ, I really enjoy this seminar series. It's a really good idea. And I hope I wouldn't forget it so often, but I always have a lot of fun listening to the talks. It's really, it's like a replacement for going to many meetings, and I really do enjoy it. So, okay, so simple materials. Let's see what these mystery materials are. If I actually, let's see, my button doesn't work to move this. Here. I cannot move. Here we go. I have to use my mouse. So it's definitely not this one, even though, yeah, Mukhtar is here. We did, as I consider, a very tiny contribution to this phase diagram. This is, in my view, the real mystery phase diagram. And we're still waiting until these squiggly lines and dots are connected someday. So this is not what I will talk today. What I will talk is carbon and water. And these are the materials we have spent the last few years sort of solving problems in the phase diagrams that have been reported previously. So carbon has been well studied many, many years ago by a guy that I still personally remember really well. He used to go to Gordon conferences, and we used to canoe with him. He was a wonderful person, Francis Bundy. He almost became 100 years old. And he was one of the first to systematically investigate the phase diagram of carbon. Can you see my mouse, yeah? At all?
Yeah, that's clear.
Yes. Mm-hmm.
Okay, so he investigated, and also together at the same time with George Kennedy, the phase diagram of, or the phase boundary between graphite and diamond up to about this temperature of 1300 centigrade, something like that. And then Bundy, with a belt apparatus, they did flash melting, electrical flash melting of graphite. And they came up with this line here, and they came up with a triple point. And he managed to get a few data points beyond that triple point and came up with this phase diagram, which you see is rather old. You know, imagine this is almost 60 years now. Yep. And I want to emphasize that since then, for 60 years, nobody ever has really measured this phase diagram up here. That means measured temperatures. You know? So this was all estimates, extrapolations, but no direct measurements. And so if we go to the next slide, there was a guy 10 years later, Van Vechten, rather unknown today. He came up with a phase diagram like this. So graphite, here's Bundy's phase boundary or melting boundary. Here's the graphite diamond phase boundary. And then he extended Bundy's melt line and said, what will happen is probably as this goes down, diamond ceases to exist. And we have, first of all, a metallic liquid that's denser than diamond. So we have a negative Clapeyron slope. And then eventually we'll turn this whole thing into a metallic solid. And this is based on the following. First of all, if you look at the group 4 elements, silicon, carbon, silicon, germanium, they, after this, have very, very similar phase diagrams. So silicon and germanium, they crystallize in the diamond cubic phase. When you melt them, they go into a dense metallic liquid, and then they go into some dense metallic state. The other base for Van Vechten's phase diagram was shown here on the right, based on very early, let me get rid of this here, based on very early shock experiments that saw transitions to a denser phase. And this was back in the 60s. So here I reversed the numbers, but this is sort of now the similarity that was the basis for these assumptions. So the conclusion was, well, diamond is not forever. The diamond field somewhere ceases to terminate, and then we will have another phase that's not known. And this is at relatively low pressure here these days. Then about 10 years later again, a guy named Shaner, who I also knew well from Los Alamos, they used their gas gun to shock, I think this is graphite. And they said they took 5 data points along the Eugonio and measured sound velocities. So this was rather new, a new development to measure sound velocities during shock. And they, of course, along the Eugonio, you will never see a discontinuity. It's just not strong enough if you look at pressure or volume. You have to measure really the sound velocities, the derivative, to see any deviation. And they said, well, our data points are all solid-like. They have velocities that we expect for the solid. And if they predict the sound velocity of the liquid, it would be a lot lower. So they basically threw out this earlier shock data. By the way, this paper is extremely short, has no details. It's published in some proceedings journal. So there's really no detail here, but there's data. Anyway, so based on this, these earlier phase diagrams were basically thrown out. Then there were further shock experiments. Bill Nellis, he did gas gun, there were nuclear explosions, there was theory, and then the conclusion was that diamond melts along the graphite Eugonio at about 300 GPa. Then using a gas gun at Caltech, Tom Ahrens and colleagues, they measured also the transition of graphite to a denser phase, and they saw a discontinuity, something denser at 200 GPa. So it's more or less all over the place. Then there were many, many papers. And I actually, once being bored at the synchrotron, I think I read most of them. Some of these have very funny titles, as you can see here. It's funny to read, and there's like very, very numerous, very contradicting papers on this phase diagram of carbon. And then there's a lot of work later on theory and thermodynamics, predictions, and I think show most of these here that were published. And you immediately see that the majority, if not all of these theoretical works, show a positive slope above the triple point here of graphite and diamond. It was also from these studies, it was well understood why there's a maximum in the graphite melting, because there's change in coordination, and that explains all this. There's like 2 other works here on the graphite melting, and they all show this maximum within about plus minus a few hundred degrees. So this was basically the scenario that we faced when we started working on this. Plus, there are a lot of shock data with the latest, technology. Amy gave a wonderful talk a couple of weeks ago on this, showing even further measurements, measuring equation of state during the shock. Beautiful work. There's data that are really hard to interpret, as Amy showed. It's not really happening. First of all, I mean, there's problems in both pressure and temperature measurement, and then it's very hard to really say which phase you make. So here's like a Ugonio, and then you have various theoretical melting curves, and you make an observation here at about 600 GPa discontinuity, and this was then interpreted as being due to melting. And later, at Livermore, there were further data saw a very similar scenario at slightly higher conditions. But again, like 7,000 to 8,000 degrees, pressure is close to a terapascal. And then, of course, you try to interpret this and construct a phase diagram, which is, of course, I mean, you have to do this, but I have to remind you, you don't know any of these phases, and you actually don't know the temperature either. But you can suggest phase behavior from these measurements. I have something to say about these measurements in general. If I clean my diamonds, sorry about this noise. Now let me turn this off here. As you can see, you can heat diamond up to very high temperatures. This is way above 1,000 degrees centigrade. So the fact is that diamond in its thermodynamically metastable state is remarkably stable. You can really heat it to, in a vacuum, you can heat it to 2,000 degrees without it turning into graphite. It's remarkable. The other consideration is when you shock. If you are in a liquid and the liquid is viscous, like here it's shown a glass. This was actually on the news today, but my slide is older. So there's a liquid glass state that who knows what looks how in a shock. So does it look like a liquid or a solid? So these are my major concerns about these ultra fast experiments. If diamond is stable at these high temperatures, it may be stable to very high pressures also, even you're outside the diamond stability field. So this is a concern that one should address more, in my opinion. So I'm in trouble here with my cursor. So now I'm starting to talk about our own experiments. A few years ago, we developed a new technique to heat samples in a diamond cell. We have now, fortunately, the suitable lasers. These are fiber lasers. You can heat a sample here on the left. You have a sample here in black. You put it on a thin insulation disc. We normally use sapphire. You put this whole thing in an inert gas, argon, pressure medium. Then you heat it up and you measure, while you're having this pulse, you measure the thermal radiation with a spectrometer. So here on this plot, these are direct data. This is not drawn with a computer. This is direct output from a oscilloscope. So the laser, as you can see, is rising almost instantaneously with just microsecond delays. Then the laser power stays stable, and then it decays very sharply. When you look at the emission with very fast detections like photomultipliers that have like nanosecond time resolution, you see there's a slight delay, which of course is due to heat capacity. And when you turn it off again, there's a slight delay. And if you want to, you can derive the heat capacity and so on. But fact is, we can keep a sample like this at a very stable constant temperature for 20 milliseconds. This is a time we chose because that's enough time to collect enough photons to get a spectrum here in red and have a very low noise curve that you can fit a Planck equation to. So you have fairly high accuracy in the temperature measurement, even in this rather fast experiment. Important, and I have shown this too, and it's a little bit hard to understand. Important is the in situ monitoring of not only the temperature, but also of the sample and hotspot position. And so all our spectrometers now, we take out the slit and we replace it with a mirror that has a small hole in it. So then you look at this small hole with a microscope and a camera with a beam splitter. So you get this hole projected on your camera. At the same time, you see the back reflected image of the sample. So here's the sample. Here's your aluminum thermal insulation. And then when you have a hot spot, so somewhere down here is the pinhole, which is here, this black little dot. And so you are sure that you're only collecting light from the very center of this hotspot. And so we take a movie while we're doing this. So we know if something shifts, we better discard that data point. Because if you measure the temperature just 10 microns over, you're lost. So this is, I think, very important to have suitable optics for these experiments. And then I think more important even is you need to test it. Put in a material that you know the melting temperature, like here sodium chloride, that has been measured very accurately here in green with thermocouples. Actually, this was done by Kennedy. And then you want to match this. If you don't match it, you're doing something wrong. So this is, I think these tests are very, very important. And 1 atmosphere tests, because you have very, very large samples and you have very low temperature gradients, are not really suitable to this test. You have to test this in the diamond cell with known samples. The other thing is you need as much information on the emission spectrum as possible. And I often criticize, even though they're very elegant, these 4-point temperature measurements. We still use all our 1,024 data points or 2,000 data points from our spectrometer. So we have all the information of the spectrum. And even here, you see, like, this is actually not a very good spectrum because you have in your spectrometer, you have what's known for these back illuminated detectors. You see this, what's called etaloning. So you have wiggly spots. And imagine you have a point here and a point there. Yeah? If you only have a few points, you have very, very different temperatures. So you have to have a good fit to the data. So you have the Planck equation and your spectrum that you take. So this is just a point. The other test is, so you take a rhenium foil and you flash heat it. So again, this is now the 1 atmosphere test. And you see what's happening. So here we heat it to 3190, 3380, 3460, and then 3537. And from here to here, you see the drastic restructuring of the surface. You see these round features. And when you then look at the theoretical melting curve of rhenium, you're just a few degrees off. Yeah? So in between here, you get your melting of rhenium. It's a really good test. Then you take SEMs, you check if you oxidized it or you have carbon in it and so on. So you have, best is an SEM and always measure your chemistry. That's relatively easy. So we did a lot of runs here. This was sort of when we invented or started using this method. We measured the melting curve of rhenium that had not been measured before. It's fairly high, it's difficult. So we put in a rhenium disk, polished in the diamond cell. Here's argon pressure medium. And then we start shooting at it and we're mapping this, and from each spot we measure the temperature. And you see very drastic changes in the surface texture when you go from one temperature to the other. And again, you measure it, you recover it, and you measure it if you did anything chemically with this stuff. So it's actually a very nice experiment. Then we went further and we cut into these samples with a FIB, focused ion beam. So this is like what we think below melting. You don't see any drastic change below this hotspot. But if you look closer, if you go higher temperature, you see where the red line is. If you look closer, you see a very sharp line of unaltered, and then what we think is a quenched melt material. Completely different scenario. Then we published this data. Rhenium has an extremely steep melting curve. We measured this earlier with another method, but this steepness of the melting curve later becomes important when we talk about diamond melting. We also did some runs on molybdenum, and we again get this very controversial flat melting curve, molybdenum. So now I will talk about melting of diamond. So I started this many, many years ago. I made many attempts, even back at the Max Planck. We tried with rhenium, and all we had was seeing reactions, and it was like on and off. So we got really frustrated with this. When I came to the geophysical lab, I had a postdoc, Lu Sheng. He's now back in China, Beijing. And he worked very, very hard in solving this problem using flash heating. He was also the one who did the rhenium flash heating experiment. And then later on, we had joining Amol, who you all know, I think. And then we got some data, but the data looked rather crazy. So we said, I think we have to look for other methods and tests, and we have to do a lot more analysis. And you all know Bianca, she's basically an Australian, and she has all these friends in Australia that are all experts on TEM and SEM on carbon. So they're really the carbon experts that you want to work with when you work on melting of diamond. So lots of collaborators now. I think this is a 10-author paper that we submitted. So there's 3 methods that I want to report here. One is straightforward. You take a piece of graphite or a piece of glassy carbon. You just put it in the diamond cell, you load argon, and then you flash heat. And look what happened. It's all, then these are all recovered. It's all like SEM or TEM analysis, all these runs. Then the other thing is, and that is something we developed in the Max Planck, looking at mineral phase transitions here in the center. You create a cavity, and Amy will know what I'm talking about, even though this is a rather primitive cavity, but it works. So relatively low laser power, laser radiation gets trapped in this cavity, and allows uniform heating of a sample. And we did this for silicates, and it's remarkable how well this works. The temperature is uniform, and you can reach very high temperatures with low laser power, maintaining stability in this whole diamond cell scenario. Then a mole, while we were at Carnegie, did a third type of experiment. That's now in the solid. So the pressure meeting is aluminum oxide powder. And we heat through a diamond disc, we heat the interface of rhenium and diamond. And then you did one shot. Each experiment for these is one shot. So it's very time consuming, very labor intensive. So these are the three types of experiments that I want to report in the next few minutes. So we start with graphite. So here you have this very old PT conditions of graphite and diamond. We did 16 experiments using graphite discs in argon. And we always had a pressure around 13 GPa. This is 13 GPa of Bundy's, plus minus about 1 GPa. And we did 16 measurements in this temperature range from 39 to 5100. And we see, in some experiment, we see nothing, and at higher temperatures, we see the formation of a drastic restructuring, which actually has been seen before by others at room conditions. So that brings us to an average temperature of this triple point of 4450 plus minus 200. The method introduces data scattered. Very clear, stability, the choice of laser power, temperature measurement, and just the nature of the experiment introduces data scattered. So just for comparison, Bundy's temperature at the triple point is 4100. Later works, more recent, is 4400. There's also some Russian work, also around 4400 Kelvin triple point. So I think this is a nice test of the system. Because it all agrees doesn't mean it's correct, but that's the way it is. Then we did graphite at higher temperatures, similar to that rhenium disc. We used the graphite disc, slightly polished as good as you can, and you take various shots on these this disc, and then you analyze it. You map it where you took the shot, you measure the temperatures, and then you see from one temperature to the next, you see drastic resurface changing. Now, it's important to say that all heating at all temperatures that we did always produced diamond. So this is it's well known. Graphite within microseconds, even in the shock, converts into diamond fully. So we always, out of graphite, make diamond. Here's the diamond peak. Here is some peak that we probably can interpret as some defects, maybe something graphitic, it's not clear, but the majority here is diamond. So we think we melt diamond and not something graphitic or some intermediate phase. If below melting, the graphite turns into diamond, and above melting, we get diamond, we think we melted diamond. That's our assumption. And so we see very drastic changes here from actually within very narrow temperatures. You make a hole or like an indentation, which is understandable because you convert graphite into denser diamond. So you make pits. And then when you melt, you have sort of melt rims. And these have, this is very similar to what was observed by others that melted graphite at high pressure. Usala, I think, is a publication. Okay, so now we come to the second method. This is this cavity heating. So again, I show this picture. We have a diamond grain, and this is a grain, I don't know if I have a scale here. I lost the scale. I think here's 10 micron. It's about a 15 micron grain that you just take out of polishing powder. they're normally, when you buy polishing powder, they're very sharp grain, grain boundary grains. So you just pick one out, and then you see the hole here, the cavity of balls, and so you have diamond, you heat it, here in this case to 3200, and you quench it, and you analyze it, and you get clean diamond. Even at 3200, there's no trace of any reaction in this. So green here is rhenium, red is carbon. So very clean diamond. So we're chemically rather clean. However, not always. Lu Sheng did at least 100 experiments of that sort. And very often, that grain shifts during the pulse. Imagine you're in liquid, in very low viscosity liquid argon at these conditions. So often the grain shifts, that reduces the quality of the temperature measurement, and it also often we have reactions then when it shifts to the wall and the wall shows partial melting or whatever, you will see chemical reaction. So out of about 100 experiments, we discarded about 70. So it was very hard work. But nevertheless, oops, I can only use my scroller my cursor doesn't work. Wait. So this was the previous. Now we go to a higher temperature. Oops. So we go a few hundred degrees higher. We still get fairly decent Planck spectra. I mean, the quality, the misfit would represent maybe 200 degrees, not more. So out of a grain again here, before heating, you heat it to this temperature and you make a sphere. Now, why do you make a sphere and not a beautiful single crystal octahedron diamond? We can only compare this with a material that we all know. When you flash heat ruby, you make ruby balls, and we use ruby balls all the time, and it's crystalline, and ruby does not turn into a glass. So again, you make perfectly spherical ruby balls. I have done it. It's fun. You just shoot a laser on a piece of sapphire, a piece of ruby, and then you have a slide underneath, and you collect all these beautiful ruby balls. The chemical analysis shows that the majority of this ball is carbon. You have some splashed rhenium on it, but I would say the bulk of it is still carbon. And again, the Raman spectrum from that shows that it's clearly diamond and not some exotic material we made. Then a third method is what a mold did. Again, here we heat through the diamond, through the aluminum oxide pressure medium, through the diamond, and heat the interface of this rhenium plate. And then we take this apart. So it looks like a beautiful birthday cake here is basically, you see this portion is the diamond. We peel off all the aluminum oxide powder from the south. So you see this piece is diamond, and underneath here you see the rhenium disc. Okay. So I molded 24 experiments in 2 series at 30 and 50 GPa. And this is the temperature span of these runs. So again, a lot of work. And then you take it and you fib it. So I think this was done in Melbourne. Part of it was even done in geophysical lab when we had a working fib sometimes. But the majority of these runs was sent to Australia. And so here's this disc on the left that I just showed, and you do a fib cut, and then you look what happened. So you see here in black, top is diamond. It's strange, the coloring here. But at a certain temperature, you have a very sharp interface. If the diamond had a crack develop, of course, rhenium will go into the crack because rhenium is still a ductile metal and it's hot. but it doesn't look like you had a melt going in there. At higher temperatures, the following happens. We erode away the diamond. And I will show in a second that we then recrystallize it, and these balls, these little crystals are pure diamond. So we do something to the diamond. And if you look at it chemically, we do not make a carbide. You immediately see it in the TM analysis. We make pure diamond and not some carbide. It's important for this run. Years ago, we did this without flash heating, and you immediately, in like a second heating, you make rhenium carbide. But obviously, the time of 20 milliseconds is short enough to avoid this. This is quite interesting. Okay, we look at these products and we home in, we then thin it and do a fib analysis, a TM analysis, and we see that this is absolutely pure diamond, you know, with no rhenium in it. So then these are the results, and it's crazy. Yeah? So we, of course, have lots of data scatter. There's many methods. This is difficult. It's not much worse than if you do a laser shock experiment, as we have seen. You know, nowadays we sort of, the time of cherry picking is over. So when you do something in the diamond cell, you just get, things become more difficult and produce higher uncertainty. But I drew a line in here. So just to go back on the data, this is our range of triple point measurements. And so I chose a point here, it would be the triple point slightly higher than others, but almost the same as others. But then I draw a line here, which is above this line, there is no solid points. They're all below. And if you would be bold enough to do a melting curve, it would probably go down here somewhere. Very strongly negative. So there we are. And of course, now you send this out for review and you face all these people, you know what you get. So this is pretty interesting, but I think it's rather solid data. People have to sort of check this out. Good luck. So I will move on as we move from diamond, we then move to water. So I will talk about our latest work on how we solve the water ice phase diagram. So going back in the history, like a lot of people did melting of water or ice, so ice 7. You know, you can easily make ice 7 in the diamond cell. You heat it up, you X-ray it, you take a Raman. I have to emphasize that if you look at the data, of course, both X-ray and Raman measurements to determine melting are extremely difficult, and the signals are weak and the transitions are hard to see. But nevertheless, there's at least half a dozen estimates that measure melting curve along here. So this is the line that was accepted quite a few years. And then we started doing this using a method that we have used extensively, that we well know and well trust. So you take, you load your diamond cell with water. Then you put in a piece of, we normally use iridium, which does not react with water. And then you heat that with your laser. And at the same time, you shine another laser, like a blue laser, gives you a laser speckle on the surface. This movie doesn't work right now, but you have seen it. It moves and you see both solid-solid and solid-liquid transitions very easily, very reproducibly. I really encourage anybody that wants to have fun in the diamond cell to do this. This is really fun. But what we get is completely different from others. So we see here the red and green. So these are two different publications using slightly different detection methods. One even uses an infrared indium gallium arsenide detector to get lower temperatures. But we get melting curves that deviate strongly from the previous ones. But the important thing is that we see a kink in the melt curve, right here. And this is hard to discuss away. But when you think about it, the prediction was that I7 eventually goes to what's called symmetric ice 10, which has structure like an alkali halide. That at some pressure here, people have seen again extremely weak evidence of a transition from I7 to something different. There's many estimates here. I haven't bothered showing all the authors here. There's lots, but that's what we get, and we think that this transition or this kink that we see is probably a triple point from this I7 to this I10. Then we went back and looked closer using this method, and we saw an additional very clear change in the speckle pattern that indicated a solid-solid transition. And it's very reproducible, it's easy to see. And when you approach this pressure, you no longer see it. And so this is the base for drawing up this phase diagram. So still lots of controversy. The suggestion for ICE10 was that this may be a second order transition. But then again, if you see a kink in the melting curve, it cannot be a second order transition. There must be a volume change here at this point. And of course, all this is related on the big question, is there a superionic phase somewhere that would be very important for like conductivity in planets and such. So this, in my opinion, this phase diagram is not solved. And so we did further measurements, and this was done with Mukhtar. This is probably the most beautiful measurement for melting of ice, because when you do brouillon and you heat this up, your solid peak disappears and you have a liquid peak. So it's really not like the subtle change of some Raman spectrum or some diffraction pattern. This is really a sharp transition. So you pin down the melting really clearly. We had a lot of fun doing this together. This was very hard work, but I argue that again at this pressure you see some sort of kink and this melting curve moving up. And of course beyond that, the heating and the measurements, this is very difficult. It becomes almost impossible to do a brouillon with laser heating. So this is like a externally heated diamond cell. Again, so it's still not very clear. So now I want to talk what we try to do in solving this phase diagram with new methods. I don't know if all of you know that the United States has the world's strongest neutron source in Oak Ridge, Tennessee. It's I'm right now sitting right somewhere here. It's on a hilltop, it's beautiful. It's not only the location of the lab is nice, you have nearby what's called the Smoky National Forest. And here on the right, what looks like a postcard, actually I took on my birthday a year ago. It was the most spectacular sunset I've ever seen. So this is a great place to be. So neutrons, these are really strange beasts. You're all familiar with X-ray diffraction. So you hardly can see hydrogen, carbon is hard, oxygen, and so on. And the heavier you get, it's very systematic. The more electrons you add to the atom, the better you see it with X-rays. With neutrons, it's completely different. You're looking at this thing. You're looking at the nucleus. And so different nuclei have what's called different coherent cross-sections. So I don't want to get into this. This is not easy to understand because it's isotope dependent. So you have all these different cross sections. Look at hydrogens, very strong. Beryllium, carbon are very easy to measure. So this is the method of choice to measure these things we are interested in. You know, hydrogen, hydrides, carbon materials, and so on. Things with oxygen in it. All these things that are hard to see even at a synchrotron are very easy to see with neutrons. However, if you look at neutron sources, and here's SNS, the fluxes are rather low. Even though we're the strongest source in the world, we are not even approaching the photon flux from a 60-watt bulb. So right now we're sitting a little bit higher. You know, 2020, we're probably a little bit higher here because we changed the input power of the accelerator. And so on the right, you see, I mean, what's happening over the years, the development of pressure. Maximum pressure in the synchrotron goes skyrocketing up to terapascal now, whereas neutrons really were always very low. And so our main effort was to break out of this, to change this. The problem is the problem due to this low flux is the following. You're used to this. You do X-ray Raman, and this would be your sample. If this would be a sample like 20, 30, 50 micron, to see anything with a neutron, you need a sample about of that size, 0.05 cubic millimeter, or otherwise you just see noise or you collect for months. So this is the problem. And so you say, well, I just use bigger diamonds. And when we started this, this was before the development of the growth of very large single crystal diamonds, the availability of single crystal natural diamonds. It was just skyrocketing in price. So we worked with this company, the CVD technique to make large animals was actually mainly developed at Carnegie. So this was a spin-off. And what you're looking at here, the largest animals are like 10-carat diamonds. And again, for most of people, this is very hard to afford, but we did it. It's a national lab. You get the proper funding and you can do this. So just for a comparison, the crystals that they grow now are over 30 carats large. So you have this, but then I ask you, even if you have large animals and you need a large sample, what would you go to which pressure would you go if you had a 1 millimeter QLID? So each of you can sort of say, maybe 5 GPa, 10 GPa. So it's probably something that we haven't thought of. So we went out to solve this problem, and this took like 10 years to I started with Malcolm at Carnegie over 10 years ago. We worked with Antonio, Jamie, and Chris, Antonio, Jamie, and then later Bianca joined. So we sort of developed this team to break out of this problem of neutron diffraction above these very low pressures. So we developed new cells. The cells are not what you have in your lab. Even though the size is not much different, we had to change the strength dramatically because now we need, on a 1 millimeter QLID, you need 10 tons of force. You're probably used to a cell that needs maybe 100 or 200 kilograms. We need at least 5 times more, 10 times more. We need because we have this high force, we need components with very high stability. So very massive, very precisely machined materials. And then we need, because we're dealing with neutrons, and we need large apertures, which is no big deal. We have this in other cells, but we need larger apertures than in conventional diamond cells. And then we can only do this with CVD animals. We can't afford any natural animals that are like multi-carat. We started out with culettes of 1.5 millimeters. We built these cells. We even made extreme cells with very, very large apertures for not only diffraction, but also inelastic scattering. But I'm not talking about that today. I think Bianca showed some data. So what we did, of course, the facility is a user facility. So the first task to make a system that works for users. And so we came up with this solution, diamond cells with that can be spring loaded, or I later showed we have a press. We provide the diamonds. So we have to provide everything here. A user cannot bring his own cell, for example. And a user normally will not be able to buy these diamonds that cost many thousands a piece. But that's not the only problem. The other problem is these cells activate in the beam and you are not allowed to take them home. So we have to have a whole bunch of these made that stay in a safe place in the lab so we can reuse them there. So we have a very large Q range, and then we actually, these are the first tests on nickel. And now we're getting data that are almost like synchrotron-like, very sharp peaks, very high resolution due to this large aperture. There is one major problem is when you use large anvils. You go through a lot of diamond. What is shown here, Malcolm Guthrie, he did this to demonstrate what's going on here. So you're going in with a wide beam, but then due to Bragg scattering, you lose a lot of energy. And this is well known when you do X-ray absorption at synchrotrons, and you go in with wide beam, you lose a lot of intensities at various places. And this is shown here. So we measure this. We measure the time of flight, and we see that there is large, what we call dips. These are due to this Bragg reflection intensity loss. The worst thing is, the more you squeeze on this anvil, the more severe this gets. So this is it was a major, major problem if you want to derive like a structure of ice, where we are heavily dependent on the relative intensities of the peaks. So in order to solve this, you measure this, and then you make here this is in D spacing, so it's similar to this in the time of flight. So you see this diamond correction here that we know how we must apply this to our spectra. So this is on D2O ice. So in red is without the correction. And you see that here in the 111, you have an almost 20% correction. And it makes a huge difference in the relative intensity of the peaks. So the correction is essential in these experiments. So neutron diffraction is not like what you do at HPCAT, where you have monochromatic beams and the diamonds are small. And this is a very tricky kind of data reduction. Right now, Malcolm is the only person that can do these corrections. And so he's training others. So it's rather not straightforward. Nevertheless, we go back to this phase diagram and we see what's going on at these pressures. Do we see this famous ice 10, this symmetric ice? I have to mention that for neutron diffraction, we have to use deuterium because we have very strong scattering of hydrogen. So we use D2O ice where the transitions are not known where they are. So we go to always like 60, I come to that. At 65 GPa, that was always our limit, but we can measure the proton distance. So this is now the absolute unique thing that you can do with neutrons. You can measure this distance of the protons. And then we plot this. So here's the average proton side separation. And so we plot this, and we get this curve. And these are some theoretical stuff, also from earlier lower pressure experiments, so it's good agreement. And so when we plot this, we predict that about at a megabar, we have a full symmetrization of ice. But we always break diamonds at 65 GPa in every run. So it was very puzzling. So we had to do something about this. And fortunately, we were lucky. We had at SNS, we had major upgrades. First of all, compared to when we did this, we have now almost double the accelerator power. It's now routinely at 1.4 megawatts. The accelerator, by the way, is here. The experimental building is here. So you have like a synchrotron-like storage ring, and then you pump your protons into liquid mercury to create spallation neutrons. The other very important upgrades was the beam guide. So you have no focusing physics for neutrons. You need to guide them, and these are tubes with super mirrors in it. So they just, the proton or the neutrons bounce around here so they don't diverge like crazy, and we have the highest flux neutrons where we want to have them at our sample. Here are the detectors. They were also upgraded, which made a big difference. And then we built new diamond cells. I'll show this in a second. And then we switched from these cheaper CVD anvils to real gem quality CVD anvils. Of course, the price is like triple. And then we used something that also everybody thought was crazy. We use rhenium gaskets. Now, rhenium is not transparent for neutrons, but I'll show this in a second. I'll show it right here. So here's our anvil. This is actually from the last run. These are 600 micron culettes. This is a disc of rhenium. Now, as you all know, when you squeeze on this, it sort of tilts and flops and bends. So we have a support for this made out of aluminum wedges, here in bluish. Aluminum almost has no absorption of neutrons. So we keep this in to keep this disc as it is here. And then when you look at the detector position, we only have a very slight shadowing of our detector areas. Most of the signal from the sample is still seen by the detectors and not obscured by the rhenium disk. And the data on ice, we had this at, again, like 60 GPa. We see that we have very beautiful data even in this rhenium gasket. Now, you all know the previous material for these neutron experiments was stainless steel. You all know stainless steel is like chewing gum. It's far too soft. It's not really the material to use. So rhenium is a lot better to go to megabar pressures. So we build a new cell, and just like a few more words on that. Again, you have these type cells. They're still like pocket size. They're like just 2 inches in diameter, 3 inches long. And then I discovered something in the industry which is fairly old. We all struggle always with when we use piston cylinder apparatus. So the joke is they're either too tight or too loose. Now, if you go with this tonnage on your diamond and you have a few micron shift here, you immediately break it. So we need very rigid guiding, and this is a perfect, very cheap commercial product. So all our cells are now constructed like this. So we have a carbide piston here and a sleeve here in red. You buy all this and it just fits. There's 0 micron wobble, and the great advantage here is this will also work at low temperatures. You don't freeze up your cell. Then I sort of changed the diamond design, because now we're using gem quality diamonds. They're a lot more expensive, so we had to reduce the size. And then I built this funny looking scenario. You have a binding ring here in gray, and you leave a little gap. So as you squeeze on the diamond, you increase the radial support until you bottom out on your carbide. And I took this anvil to 9 tons without it breaking. So this actually works. This is now what we're using. Then we built this hydraulic press. Bianca showed this already. So we have in situ pressure change. This is hydraulic. It's still not very big. It's easy to handle. It goes to 20 tons. And then we collected the first data. So Bianca and I, we got in during COVID. It was just a few weeks ago. And we said, let's choose the first material, graphite. As you again see, for X-rays, graphite is very hard to see, not only because the X-ray cross-section is small, but also you go through your anvils. And for neutrons, this is a lot different. You have, here's carbon with very high cross-section. And as you can see, if you have 1 atmosphere graphite, it's a very strong peak in relatively short exposure times. But then as we squeeze on it, we observed a very drastic reduction of this peak intensity, and it eventually goes to 0. And then we break the diamond. And this is well known. And people, I think they're now in the audience, they know this really well, that you make something very hard when you squeeze on this sort of graphite. And because it's so incompressible, you create ring cracks on your culettes. That's what happened. So I think we're still analyzing this. So we see this amorphization, I think, very clearly. You would not see it as clearly with X-rays, definitely. But this is very beautiful, in my opinion. And then the second run was now really pushing it. So we reduced the culet size to 600 micron. Our sample is still 300 microns big. The beam is 250 microns. And here is what we get. So when we load this up with 5 tons, we reach 1.2 megabar. And so now you get your answer. What will I do with a 1 millimeter culet? Well, with a 600 micron culet, you go over a megabar. And the data are very beautiful. So I'll show you in a second. You see here the shift of, I'll just use one peak. So you see the shift of peak, and if you look at the highest pressure, you see more noise. Very easy to explain. All these were taken 5 hours long, and here in the highest pressure at 1.2 megabar, the anvils disintegrated after 1 hour. That's why the spectrum is not so good. So then Malcolm, we sent the data to Malcolm, and he started to refine them. This is now for an earlier run with 800 micron culets at around the megabar. So it's beautiful, refinable quality data. So these are 6 different detector portions. We have not even summarized this. This would even look better if you put it all on one plot. So I think we're very, very happy about this. This gives us now, I think, a good starting position to get neutron diffraction out of its baby stages. It's not only this, we have like a very fantastic future. We have completely new devices being built. One is in Sweden. It's under construction. It's nearly finished. It will start to operate in just a couple of years. At Oak Ridge, we have, here's the old station. They're planning to build a second target station. Now, these machines have a multiple of fluxes of what we have now. So my hope is that I will see a similar development. Like, I'm sort of a synchrotron man of almost the first hour. I did my first synchrotron run, I think it's 32 years ago. And we were at a first generation synchrotron. And the exposures were about 5-6 hours like we have now. And then the development came, and now we're into the second or even millisecond exposure times. I think with neutrons, we will never reach this, but we will be in a much better shape to do what we really want to do. Not only that we go multi-megabar pressure, we also can then use smaller intervals to make this more affordable for everybody. So I think neutrons have a great future, in my opinion, to look at these things that we are all interested in. And that's all.
Thanks, Ronnie. Great talk. And actually, you broke a record with attendance. We had over 150 people participating.
Oh my God.
You broke Kanani Lee's record.
Thank you very much.
Questions for Ronnie? I'm sure there are quite a few. Just unmute yourself or use the chat.
So what do I do? I stop? No, I still leave this on, right?
Any questions?
Hello, Nilesh here. I'm a postdoc in UIC working with Professor Hamley. My question is regarding the high pressure neutron studies you did on the nickel. Is it a hydrostatic or non-hydrostatic?
This is non-hydrostatic. We have not done this yet because we're still exploring sample sizes. We do have we have built a gas loader at Oak Ridge, so we're capable of doing gas loading. We even look at hydrogen. It's another project. So this will be done in near futures.
Thank you.
Hi, Ronnie, it's Burkhard calling. Very nice talk, I enjoyed it. Can you go back to your final water phase diagram of water that you presented? I may have missed the last slide because I had to step out.
Water. This one.
This one. So what are the theoretical people who do have initial simulations? Have they proposed anything that's happening with the blue dots and the green dots? What's the theory of initial context? I have not worked on this recently. So.
Okay, I'm familiar with one piece of work from Livermore, and they're up here. I have not really, I think there's nothing really much recent on theory of this. But there's one piece of work, I forgot the author, sorry about that.
What's striking though there is that the very first prediction, this 1997 prediction that you show there on the right, is suggested that you would see something like this below 50 GPa. So there's some consistency with theory.
Well, I mean,
specifically, I'm asking is there any evidence? You can imagine an I7 to I10 transition that leaks a kink on the melting line. I agree with you on that. But is there any merit for a theorist who starts a new PhD project to look for a new phase between the blue line and the red line that you have? Or would you say that's just not, the blue data point are obsolete altogether?
Well, so, definitely. We're very confident about the solid-solid transition. Nobody has seen this. You need this. But we tried Raman and X-ray. We didn't see anything. So it's very hard because, I mean, water is a poor scatterer. It's also Raman signal's weak, especially when you heat it. That's probably a place for theorists to check this out. You know? Now.
So, Ronnie, this is Eric Schwegler.
Yeah.
Just to differentiate myself, I'm not Schwager. I'm the Schwegler. So I'm the theorist.
I know that.
I'm the theorist that looked at it a long time ago. So so yeah, there was. We did a lot of two-phase melting simulations with ab initio MD back then, in this range, and it looked like there was a kink that was consistent with the Schwager data that you have there. You know, and that was a long time ago, though, and I think, you know, as Burkhard was saying, I think that this is an area where somebody could probably go in and do a better job these days from the theory side and see if they could describe some of these in more detail.
Okay.
But that's the paper. It's a PNAS paper.
Yes, that's the one I think I referred to.
Yeah.
Now, I have to say, I want to encourage the experimentalists through you. If you want to do an easy experiment, do this one. This is so easy. It's so much fun. Now, we spent a lot of time on this because we deviated from all these people. We said, what is going on here? What are we seeing? So we went and did chemical analysis. We synchrotron. We went to the synchrotron many times with the system, looking if there's reactions. And we were very confident that this is the answer of melting. So I encourage people just to repeat this and maybe do other measurements or expand the Brouillon measurements. So Mukta and I talked about this. There's ways possibly to do this. Theory, of course, I mean, I don't know much about the difficulties in these kind of systems with hydrogen. When I asked Scandolo, you know, who published this bottom superionic state, and said, I asked him, what is a superionic state? He said, I have no idea.
Hi, Ronnie, this is Alex. How are you doing?
I'm good, thank you.
Yeah. Okay, so there are two sets of data. One is published recently in parallel, and there is a data published in archive by Prokopenko et al. I encourage you to look at this data, which suggests that there is a superonic phase somewhere where you're showing.
I'm familiar with that. Yes, yes, I saw that. Yeah. By the way, these are your data points, Alex.
Yeah, thank you.
Sarah Arvidsson has a question. You want to ask it?
Yes.
She's asking about the rim on the melt that appears lightly colored in the SEM images.
The what?
There's the rim structure that appears in your SEM images, and she's asking about that.
On the graphite?
Yes.
This here.
Is that what you mean, Sarah?
Oh yeah, okay, I think I'm unmuted now. Yeah, so that shadowy rim that we see at 4031 Kelvin there, I've seen it in some other metals and semiconductors, and it usually looks compositionally similar, if not identical to the melt. So I was just curious if you had any explanation of what's going on there.
We puzzled about this. There's a nice paper by Musala, I think. He saw exactly the same in graphite, and he does this up to about 2 kilobar, and he argues about what this is. So the quenched melt, I don't know. I cannot comment more on it. It's speculation. I mean, what we mainly did here is you go from here to there, you know, not maybe put too much attention what really physically happens here. It's just you want to see discontinuities. But it looks like quenched melt of some sort.
So on the diamond melting question, I can see why you're running into problems with publishing this, since it is so different than 20 years of work up to now. But if you take at face value that your negative sloped line there is correct, then it has implications for the thermodynamics of the whole system. So I'm wondering if you've worked through that, you know, in terms of the densification of the melt and so on, and whether it makes sense thermodynamically, or what the structural implications are for the other thermodynamic properties, what the implications are for that.
We had a very strong argumentation by one of the reviewers exactly about that it sort of contradicts our thermodynamic understanding of this phase diagram. I think the main problem with this is that you have to assume that the melt is denser, yeah? And a lot of theoreticians have a problem with that.
That's right. So,
Melt
how much denser would it need to be, for example, given the entropy change?
Well,
melting.
I mean, you could probably derive this directly from the silicon and germanium data and from the Clapeyron slope. I don't know. I didn't put the numbers. I haven't gone through the numbers, but the slopes are very similar. So you must have similar delta V's in the solid to the liquid. I mean, all the argument hinges about the density of the melt. And if you look at all the later theoretical work, they all say this is not possible. And
I can second that. We worked on this for our initial simulations, and in our liquids, the density is always lower than that of diamond. Diamond is dense, so making a denser liquid is hard. But I'm not, this is, the ab initio data is inconsistent what you found. It just makes it interesting.
I'm fully aware that this is very controversial. We literally spend years on this. This is what we have. I will not repeat it. I mean, I think it's rather solid data.
More questions for Ronnie? Okay, if not, thank you very much, Ronnie. That was a great talk.
Thank you very much. Yep.
Thank you all for joining us.
Thank you.
We'll see you next week.
Bye-bye.
Bye-bye. Thank you.
Bye, thank you.
Thanks, Mukhtar.
Yeah, talk to you later.
Yes, okay.